It's nearly impossible to balance a pen upright on its point, though it's easy to stand it upright on its flat end. The base of support is inadequate for the point and adequate for the flat end. Also, even if you position the pen so that its center of gravity is exactly above its tip, the slightest vibration or air current can cause it to topple. What happens to the CG of a cone standing on its point when it topples? The CG is lowered by any movement. We say that an object balanced so that any displacement lowers its center of gravity is in unstable equilibrium. A cone balances easily on its base. To make it topple, its CG must be raised. This means the cone's potential energy must be increased, which requires work. We say an object that's balanced so that any displacement raises its center of mass is in stable equilibrium. A cone lying on its side is balanced so that any small movement neither raises nor lowers its center of gravity. The cone is in neutral equilibrium. Equilibrium is unstable when the CG is lowered with displacement. Equilibrium is stable when work must be done to raise the CG. Equilibrium is neutral when displacement neither raises nor lowers the CG. For the pen to topple when it's on its flat end, it must rotate over one edge. During the rotation, the CG slightly rises, then falls. Toppling the upright book requires only a slight raising of its CG. Toppling the flat book requires a relatively large raising of its CG. An object with a low CG is usually more stable than an object with a relatively high CG. The horizontally balanced pencil is in unstable equilibrium. Its CG is lowered when it tilts. But suspend a potato from each end, and the pencil becomes stable because the CG is below the point of support and it's raised when the pencil is tilted. The toy is in stable equilibrium because the CG rises when the toy tilts. The CG of a building is lowered if much of the structure is below ground level. This is important for tall, narrow structures. The Space Needle is so deeply rooted that its center of mass is actually below ground level. It can't fall over because falling would not lower its CG at all. The CG of an object has a tendency to take the lowest position available. A table tennis ball is placed at the bottom of a container of dried beans. When the container is shaken from side to side, the ball is nudged to the top. The same thing happens when an object is placed in water. If the object weighs less than an equal volume of water, the object is forced to the surface. The CG of the whole system will be lowered because the heavier water occupies the lower space. If the object is heavier than an equal volume of water, it'll be more dense than water and sink. The CG of the whole system is lowered. When you stand upright with your arms hanging at your sides, your CG is within your body, typically 2 to 3 centimeters below your navel and midway between your front and back. Raise your arms vertically overhead. Your CG rises 5 to 8 centimeters. Bend your body into a U or C shape, and your CG may be located outside your body altogether. A high jumper executes a Fosbury flop to clear the bar while his CG nearly passes beneath the bar. When you stand, your CG is somewhere above your support base, the area bounded by your feet. In unstable situations, such as standing in the aisle of a bumpy riding bus, you place your feet further apart to increase this area. Standing on one foot greatly decreases this area. In learning to walk, a baby must learn to coordinate and position the CG above a supporting foot. You can probably bend over and touch your toes without bending your knees. In doing so, you unconsciously extend the lower part of your body so your CG, which is now outside your body, is still above your supporting feet. Try it while standing with your heels to a wall. You're unable to adjust your body and your CG protrudes beyond your feet. You're off balance and you topple. You can lean over and touch your toes without toppling only if your CG is above the area bounded by your feet.